We are all set, so please, the floor is yours.
Good afternoon, everyone. I'm so sorry. I wasted a lot of time to figure out this problem. So it's a great honor to be here to celebrate the 15th anniversary of the establishment of the group. I think Marco is on site. Eugene is on site. Pedro, Miguel, and also Juan Carlos, Helgi, Carolina is on line, right? So really very nice to see you, although I cannot really see. So I'm gonna to briefly, I'm gonna give a very brief and a very quick report on some piece of my recent works. In particular, the works I initialized when I was a PhD student in Avila. But before that, so Carlos, please, yes, the next page. So first, I would like to briefly introduce myself. My name is Mengjie Wang, and I was a former group member. Actually, I went to Portugal in 2010, first as an exchange student in Mengjie University. But at that time, there was nobody working on gravity and black holes in Mengjie. So I was introduced to Porto. At that time, Carlos was in Porto, and we start collaboration since then. And during my PhD, I work with Carlos and with Marco on various projects, such as Hawking radiation, spool radiance, and black hole quasi-normal modes, which I'm going to talk later on. Actually, it's not an easy thing to get PhD abroad, so I got a lot of assistance from the group members. And in the bottom, these two figures, these two pictures, actually I got from the group website. One is when I was defend my PhD thesis. Another one is when I gonna leave. So yeah, time flies. Okay, next slides. Okay, so in the following, I'm gonna very quickly introduce some pieces of my works. One is about black hole quasi-normal modes. My interest on black hole quasi-normal modes is originally started from my PhD in Avila. As most of you probably knows, quasi-normal modes are believed as the so-called characteristic sound black holes, and technically it is eigenvalue problems. And quasi-normal modes has been explored in various ways in a lot of context. And the reason is that for asymptotic flight black holes, by studying quasi-normal modes, one may test gravitational theories in the strong field region by gravitational waves. And in asymptotically de Sitter spacetimes, one may test so-called strong cosmic censorship by using quasi-normal modes. And in asymptotic EDI spacetimes, quasi-normal modes can be used to explore the strongly coupled systems. And there's a lot of things one can do in this field. And for me, what I'm interested in are two things. First is boundary conditions. This is exactly started with when I was PhD in Avila. The thing is, in asymptotic ADS spacetimes, the mostly implied boundary conditions is so-called Dirichlet type, but it's very restricted for high-spin fields. This kind of boundary conditions cannot be applied. So we have proposed a new one, which is Robin type, and we call it vanishing and flat boundary conditions. Another thing I'm interested in is the methods. In order to explore block question number modes, one has to resort to numerics. And there's a lot of methods, numeric methods already existed in literatures. And each of them has advantages, disadvantages. And one thing cannot be well explored is to study the so-called highly damped modes. And for this issue, we have constructed a new method, which we call it is Schoen-type function based. This Schoen-type functions, including generic Schoen functions, complement Schoen functions, and double complement Schoen functions. So, Carlos, please next page. So, for the boundary conditions, we have explored various cases, including scalar, Dirac, Maxwell, gravitational cases. And we found two interesting things. One is for vector perturbations, we observed the so-called spectrum bifurcation effects. And for charge fields, we observed the anomalous decay pattern. Anomalous means that the fundamental mode decay faster than the excited modes. Next page, please. And for the numeric methods, we called the Schoen function-based numeric methods can be explored to the highly damped modes. Here we gave an example. The left panel is for the result obtained by the existing method. As you can see, it is not complete. Because the modes is cut off on the imaginary axis, but our method can across its imaginary axis. And in particular, we can observe the so-called exception points. And we know that for non-Hermite system, except the existence of exception point is a characteristic for such system. And use this method, we can reproduce such kind of a pattern. Next page, please. And the next thing I have done is about holograph superconductors. And as most of you probably know, holograph superconductors can be constructed through spontaneous U1 symmetry breaking by black holes. And such kind of a model provide a new perspective for high temperature superconductivities. And if I remember correctly, this model was first constructed by Grubers through considering a Bailey-Higgs model. And to explore such kind of models, there's, of course, various methods. Most of them are numerics. Here I list one by using Schutting method. But in order to get more physical intuitions, a net method are also constructed. And the most used one is a Sturm-Liouville method. But for this method, it can only be used to explore the fundamental modes, cannot be explored excited modes. So to address these issues, we have constructed this method by adding more higher order terms in the trie functions. And through doing this, we found that this method can be generalized to explore exciting modes. Carlos, please go to the next page. Yeah. And here I show a few results. In the top, it is for scalar case, and in the bottom, it is for a vector field. And as you can see, whatever for scalar and the vector case, the numeric results are consistent with a net result, which shows the robustness of the Sturm-Liouville method. Next page, please. And well, I'm gonna close here and show some future directions in the context block question of modes. The first result we have obtained is for static black holes, and one may wonder if such kind of things will be happened in rotating background. And the answer is yes or no, yes and no. We have some very primary clues that this kind of things would be happened for rotating background, but not in a way as we expected. And the second thing one may explore in the context of black quasi-normal modes is the so-called exception points in other systems. In other systems means that now we only know exception points for asymptotic flight spacetimes, but for other black hole systems, it has not been observed or reported yet. So I think these things are deserve to study. And in the context of holography,
Hello, Mengjie.
so I'm wondering if such kind of things can be utilized to study. Hi, Kailash. Can you hear me?
It was cut for a few seconds, the sound, but it's okay now. So please keep on going.
Okay. So we are wondering if such kind of general boundary conditions can be used to explore holographic superconductor of strange metals. Another thing is that all the current studies is more theoretic. It is a issue how to construct more real model to whatever predicts or to study the properties of the holographic superconductors. The last thing I would like to mention is the application of artificial intelligence to black hole physics. And as some of you probably already know, such kind of things has already been applied. For example, in black hole quasi-normal modes, the so-called phase-informed neural networks has been applied, and it works. Somehow it works. And in the context of black hole images, model called branch correction diagnosing diffusion model, which is constructed by some researchers in our group, has been applied to generate black hole images, and it seems that it works very well. So I think the development of the techniques like artificial intelligence becomes more and more relevant in black hole physics, and I would like to draw attention on this trend. And yes, and that's all the things I would like to report. And thank you very much.
Thank you very much.
So I'm going to stop here. Yeah.
Thank you, Wang, for your contribution. Actually, Wang, as you've seen, is a kind of map of his kind of case, because he went to the University of Minho, tried to go to the University of Porto, and ended up in the University of Aveiro. But that's very interesting. So, Mengjie, thank you very much. It was a pleasure to see you, and I hope that we can meet in person soon. Either in China or somewhere else. Let's hope that can be that can happen in the near future.
Sure. And I also would like to take this opportunity to invite all you guys to visit our group when you are available. So it's much better than online conversation and talk. So let's see if there's such opportunities in the future. But if you have time, please let me know. Yeah.
And you will be glad to know that during your talk, actually, Marcos Sampaio entered the room. So he's here now, and I'm sure that you'd like to send him your regards.
Where is he?
So Marco worked quite a lot with Mengjie during his PhD. So nice to see you, Marco, by the way. Okay, so thank you very much. We have to